UT spot, UT scanning, and UT corrosion mapping, advanced ultrasonic techniques for material inspection. Introduction to ultrasonic testing, UT, why UT spot, UT scanning, and UT corrosion mapping exist. Ultrasonic testing, UT, is a widely used non-destructive examination, NDE, technique that utilizes high-frequency sound waves to evaluate material thickness, detect flaws, and assess corrosion. The method works by transmitting ultrasonic energy into a component and measuring the time it takes for the reflected sound waves to return, enabling precise wall thickness measurement. UT is particularly valuable in industrial environments due to its accuracy, portability, and versatility across a wide range of materials and geometries. It supports predictive maintenance programs by providing reliable measurements that help engineers monitor degradation mechanisms such as uniform corrosion, pitting, and localized thinning. Understanding the fundamentals of UT is essential before delving into specialized applications such as UT spot measurements, UT scanning, and UT corrosion mapping, each of which serves different objectives depending on risk levels, asset criticality, inspection coverage requirements, and corrosion morphology. These techniques form a spectrum of inspection intensity ranging from single-point checks to high-density mapping, enabling engineers to tailor inspection approaches to operational and safety needs. UT spot, UT scanning, and UT corrosion mapping were developed to address different inspection demands in asset integrity management. UT spot is intended for quick, single-location thickness verification and trending, typically at condition monitoring locations, CMLs. It offers fast, economical measurement and is widely used in routine condition monitoring programs where corrosion is expected to be uniform or predictable. UT scanning is applied when more coverage is needed, such as for detecting localized thinning or corrosion patterns that may not be captured by a single spot reading. It provides linear or area coverage and reveals wall loss variations. Meanwhile, UT corrosion mapping is the most comprehensive technique, producing high-resolution, full-area thickness maps that give engineers detailed insights into corrosion morphology. This level of detail is vital when assessing structural integrity, remaining life, and fitness for service under standards such as API 579. Together, these techniques form a layered inspection strategy aligned with risk-based inspection, RBI, methodologies. How UT spot works and dimensional considerations, why, when, and where UT spot is used. UT spot measurements involve placing a single ultrasonic transducer at a designated condition monitoring location, CML. This method produces a single thickness value representing that specific point. The typical contact diameter for UT spot readings ranges from 25 mm to 50 mm, depending on probe size and the recommended practice outlined in standards such as ASME Section 5. Determining the UT spot dimension is crucial, as it ensures consistency, repeatability, and comparability across inspection intervals. Engineers consider factors such as probe diameter, curvature of the surface, expected corrosion morphology, and accessibility when selecting the measurement area. While UT spot does not provide widespread coverage, its simplicity makes it invaluable for trending corrosion rates, verifying calculations for corrosion allowance, and confirming suspected areas during walkdowns. When dimensions are chosen properly, the technique becomes reliable for long-term monitoring programs. UT spot is chosen when rapid, low-cost thickness measurements are required and when the corrosion pattern is expected to be uniform. This includes straight pipe sections, simple geometries, and pressure vessels with low susceptibility to localized thinning. Engineers typically apply UT spot at CMLs identified through risk-based inspection, RBI, assessments, where factors such as process conditions, corrosion circuits, and damage mechanisms determine the most representative measurement positions. The technique is highly effective for trending long-term corrosion rates and validating historical inspection data. It is also advantageous when operators need to confirm localized areas identified through visual inspection, acoustic emission screening, or thermal imaging. UT spot is not suitable when corrosion is highly localized, such as in pitting or flow-accelerated corrosion scenarios. In those cases, UT scanning or UT corrosion mapping is preferred. Understanding the appropriate application of UT spot ensures accurate risk assessments and efficient inspection planning. How UT scanning works and dimensional planning, why, when, and where UT scanning is used. UT scanning involves moving an ultrasonic probe linearly or across a defined area to collect a series of thickness readings. This method can be performed manually, semi-automatically with encoded scanners, or fully automated depending on inspection needs. The typical scan width ranges from 25 mm to 50 mm, while grid sizes of 25 by 25 mm or 50 by 50 mm may be used for area scanning. Dimensional planning ensures that the scanning path covers all critical areas where localized corrosion could occur. Engineers determine scan dimensions based on asset geometry, expected damage morphology, and inspection accessibility. For example, pipe elbows, reducers, or high turbulence areas often require denser coverage. Unlike single-point UT spot measurements, UT scanning provides more comprehensive insights into wall loss distribution, enabling detection of isolated thinning that could otherwise remain unnoticed. This improves the reliability of corrosion evaluation and supports more accurate remaining life calculations. UT scanning is selected when broader inspection coverage is needed to identify localized corrosion patterns. It is commonly used on piping systems susceptible to erosion corrosion, flow-accelerated corrosion, FAC, and corrosion under insulation, CUI. Engineers deploy UT scanning when UT spot measurements are insufficient or when previous inspections have shown inconsistent or unexpected wall loss. The technique is also valuable when validating areas flagged by predictive analytics or inspection findings such as external corrosion or weld-related degradation. UT scanning is especially useful on components with geometries that promote turbulence, such as elbows, Ts, and reducers, where wall loss may not be uniform. It provides a balance between inspection resolution and time efficiency, making it an ideal choice when high-density mapping is unnecessary but improved coverage is essential. Understanding where UT scanning fits within an inspection strategy ensures optimized inspection budgets and more reliable asset integrity evaluations. How UT corrosion mapping works and determining map dimensions, why, when, and where UT corrosion mapping is used. UT corrosion mapping provides high-resolution, full-area thickness data by moving an encoded ultrasonic probe across a surface on a defined XY grid. Typical grid resolutions include 10 by 10 mm or 5 by 5 mm spacing, depending on the required accuracy, asset criticality, and corrosion morphology. The mapping area is determined by engineering evaluation of damage mechanisms, asset geometry, and inspection objectives. UT corrosion mapping generates detailed contour images and numerical datasets that identify pits, localized thinning, and corrosion patterns that cannot be detected using UT spot or UT scanning alone. This technique supports fitness for service, FFS, assessments under API 579 by providing accurate minimum thickness values and identifying critical corrosion clusters. It is particularly beneficial when making repair decisions, assessing remaining strength, or validating the effectiveness of corrosion mitigation programs. Determining the correct mapping dimensions is essential to ensure comprehensive coverage while managing inspection duration and resource usage. UT corrosion mapping is chosen when detailed corrosion morphology is required for high-risk or complex assets. It is extensively used in pressure vessels, pipelines, storage tanks, and components where corrosion is known to be highly localized or irregular. Engineers rely on UT corrosion mapping when assessing structural integrity for repair decisions, evaluating pitting corrosion, or preparing fitness for service reports. The technique is essential when visualizing corrosion patterns is critical, for instance, in hydrogen blistering, underdeposit corrosion, or areas affected by high turbulence. UT corrosion mapping is also deployed when validating corrosion mechanisms predicted by modeling or when previous inspections have revealed inconsistencies. Because it offers the highest resolution in UT thickness measurement, mapping is often used to establish baseline corrosion profiles for long-term monitoring. It ensures high confidence in integrity assessments, especially when operating margins are tight or failure consequences are severe. Comparison of UT spot, scanning, and mapping, decision criteria and practical applications. UT spot, UT scanning, and UT corrosion mapping form a tiered approach to ultrasonic inspection, each offering different inspection resolutions, costs, and coverage capabilities. UT spot provides the quickest and simplest measurement method but offers limited coverage and may miss localized thinning. UT scanning increases coverage and helps identify isolated corrosion mechanisms but still may not fully capture complex corrosion patterns. UT corrosion mapping provides the highest data density, enabling full visualization of corrosion morphology. Engineers must balance inspection resolution, time, cost, and risk when choosing the appropriate method. For example, UT spot is ideal for stable corrosion patterns, UT scanning suits moderately complex degradation, and UT corrosion mapping is essential for high-risk or unknown corrosion profiles. A structured comparison ensures that inspection resources are allocated effectively while maximizing asset reliability and safety. Choosing between UT spot, UT scanning, and UT corrosion mapping requires careful evaluation of asset criticality, corrosion mechanisms, accessibility, inspection history, and regulatory requirements. Engineers must assess whether corrosion is predictable or localized, whether structural integrity is in question, and how inspection results will influence maintenance and repair decisions. UT spot is appropriate for routine monitoring, while UT scanning is ideal when uncertainty exists in corrosion distribution. UT corrosion mapping is essential when high-resolution data is required for engineering assessments such as API 579 Level 2 or 3 evaluations. Practical examples include using UT spot for long-term trending of straight pipes, UT scanning for elbows affected by turbulence, and UT corrosion mapping for vessels exposed to corrosive internal environments. Applying a structured decision methodology ensures inspection strategies are fit for purpose and aligned with risk-based inspection frameworks.